Hello everyone, it's Ilya Sher from Physical Brain. Today I'm going to solve a question that's coming back in many notebooks and books, and we can find it in universities and colleges, mostly for students for engineering. And the question goes like that: a chain of mass m and length L lies on a horizontal table. The chain is allowed to slide down gently from the side of the table. Find the speed of the chain in the instant when the link of the chain slides from the table, neglecting friction everywhere. So let's draw this problem. So we have a table and we have a chain, let's say a chain made from balls all connected, some links. This is the table, and this table is smooth and avoiding friction. Now the chain allowed to slide, so we can assume somebody gave a little heat to the chain. So if this starts in t equals 0, after a while in t equals t tag, we're looking on the same table, and the chain already moved a little bit, so that part of the chain with the length x is hanging under the surface of the table. Now the question asks to find the velocity, the speed when the chain is in the air with acceleration of g. I'm going to solve it more general, and as I said, I'm going to solve it with three different principles. One from energy point of view, the second one from forces equation, and the third one, change of momentum. From energy point of view, we will assume that the height will be 0 in the surface of the table. This will be h equals 0. Now we know, because there is no friction, the initial energy of this chain will be equal to the final energy of this chain. So the chain starts in the beginning with really small velocity, because it just got hit and the chain didn't start to move yet. So it's starting, but with very low speed. So you can say in the beginning we don't have potential energy equals 0, because all the chain is in a height of 0, and also the kinetic energy is equals 0. The kinetic initial equals 0 because v is approximately 0. Now we can deal only with the right part of the equation and can say that the final energy equals to half m, while m is the total mass of the chain, half m v powered by 2, and v is v center of mass of the chain, minus mx, so part of the chain, let's say the blue part of the chain, which is hanging in the air, this would be mx, times g, times x, the length that the chain went down. But not x interesting us, we're actually looking on the center of mass of the chain, right? So we need to look on the middle of the blue part. So we replace it to x by 2. To solve this equation, I'm going to say everything equals 0, because the total energy in the beginning was equal 0. We get half m v powered by 2 equals mx times g times x by 2. Now mx equals to lambda, mass density of this chain, times x, the length of the chain. If it's not clear, go back a little bit to the theory. Lambda, it's a mass density, and it always must be constant. Now, because it's constant, it equals to the total mass divided by the total length of the chain. Parameters that are given in this question. If we're talking about part of the chain, for example, mx, part of the mass, it must go with part of the chain, the correct part. If we multiply this equation by x, we get exactly the term we had here. Let's continue this term. From here, we're going to jump down there, and we can say half m v powered by 2 equals now to m by L times x times g times x by 2. We get v equals g by L times x, root of the GL. Now the velocity when x equals L, get the form of g L times L equals root of GL. If we want to find the acceleration term, we know the basic relation is A equals dv dt. And I can change it a little bit to dv dx times the x dt. Pay attention, in this term, we get exactly the velocity. I'm going to substitute, and to get root of GL times x times dv dx. Now dv dx we can calculate from diverting this term. So we're going to get and to check this term, we can ask from the equation. So a of x equal L, we know it should give us the term of g, the free fall, and it's really giving us g, so we can be happy with the result we got. Let's check now the force solution. So from force point of view, from one side we know F equals ma from the second law of Newton, and it's equals to m dv dt. From the other side, we know that the only force that accelerating is mg. We can say F equals to mx g. And we already know that mx can be replaced with lambda x. So I write here lambda x times g. Let's put the constants of lambda. It's m by L times x times g. If we equal these two parts, two sides of F, we will get m times L xg equals m dv dt. We can see that m disappearing here. We get, because from one side, from the left side, we have x, and from the right side, we have dv dt. dt is not appropriate here, I would say. We want to work in terms of x. I'm going to play this differential game again. G by L times x equals to dv dx dx dt. Again, without changing the magnitude of this term. Inside here, we're hiding again the velocity, which is actually v. So we can replace it to dv dx times v. Now I will multiply both sides of the equation by the x. We will get v dv from the left side equals to g by L x dx. Let's solve this integral. We'll get here v powered by 2 by 2 equals g by L x powered by 2 by 2 from 0 to some x, the hanged part. And eventually we get v powered by 2 equals gl x powered by 2. I already took away the factor of the half we had in both sides of the equation. So v get the same term as before, g by l in root times x. Again, we can make the check of v while x equals l will give us root of gl, and a of x equals, the same way, dv dt, dv dx, dx dt, which leading us to root of g by l times root of g by l times x. So a of x equals l, again giving us g by l times l g. Now from momentum point of view, in a similar way to the forces, F equals dp dt. It's another way of looking on the second law of Newton, equals mx g, m dependent by x. And then we can say this side becomes d dt of mv equals lambda x times g. Now, the derivative of mv equals to m derivative of v, because the mass of the chain is constant, the total mass. We can open lambda, and m going away in both sides of the equation. We get dv equals g by l times x dt. And we can see the t is not fitting here, so I'm doing it in a bit different way. We know that v equals the x dt, and in this case we need dt, so we're going to replace dt equals the x by v. So we get here dv equals g by l times x times the x by v. And we got to the same form as before, v dv equals g by l x dx. So v powered by 2 by 2 equals g by l times x powered by 2 divided by 2. V equals, and of course again, v of x equals l equals to root of g times l. As I said, approach of momentum is very similar to the approach with the forces, yes? I just used a little bit different math. Here we played with the differentials, and down there in momentum, I decided to replace t by dx by v. So three approaches: energy, forces, and momentum.